Hello and welcome back to a new video here on the Ludwig Fussel channel. Now today it's another video devlogging my web server application that I've implemented. Now the last video we talked about the actual server, which has nothing to do with web yet at all, but it does a bit of TLS stuff if you want them to. Now today I want to go into how memory works. Now memory, if you know how long I've already taken to explain what happens in the server, this is quite less than what we have here. The allocators and the memory management is way bigger. So how do we get started? Let's maybe start first with the problem. Memory, the big old story in C++. Just use the standard template library, use new, use shared pointer, use unique pointer. Well, I didn't like anything. When I started C++, I completely did not touch the include memory at all. I didn't like the shared, I didn't like the unique pointers. Recently, I got more into them. I said, all right, okay, I do know now how to do proper memory management. So let's do it automatically. Now, unique pointer, shared pointer. You need to know when to use them and when to not use them. You need to know when a classical pointer is more beneficial than anything of this modern shit. But in the end, you have non-monitored, non-safe, non-reliable and non-fault recoverable memory management. And that's a big issue if you are writing business class or grade software. This is why some old C and C++ monoliths still exist today. Because somebody back in the days has written rock solid code that just works. That they know that the memory management works, that there are no leaks, that there is everything correctly implemented. And this is why nobody touches these and why everybody just builds on top of these. They build on top. They have a hell of a lot of mechanisms on there to check that everything is right. And that's why they exist. That's why the Java and like everything that's like garbage collected madness sometimes arises. When the application just does not perform like it does always. When the application at some point skyrockets with memory. Has the memory for a few minutes and then has a GC collection when there is like a load of requests to the server, getting slower, having some big lags because of garbage collection. It goes up, memory usage, more connections come, goes up, goes up, goes up. It kind of like caps the memory of the system. It decides to go for a garbage collection. GC is like taking up all the time. Everything lags. Bad response rates, not a good server, I don't know. There are ways around that. There are web stacks in Java that kind of like go around the issue quite at all, and they are maybe not even like prone to that errors, but still you are kind of like always having a bit of a problem with all of these memory management systems. So what I try to do is I try to implement a fast, reliable, secure, and also fault recoverable memory system. Now fast, it's C++, so it's going to be fast in general. Don't say that and don't take me into account of that. Of course, if I write custom memory management, it's going to be slower than just using plain malloc and free. I don't mean custom allocators, I mean custom memory management. It's a different thing than custom allocators, even though custom allocators can be used for memory management, which I am also doing. But you can also, of course, implement custom allocators that are way faster than malloc and free, which I have one in here but not yet used, but I'm gonna get to that. Now it's fast because we have custom allocators later on, like the pool allocator. We have it implemented in C++ in kinda a way that I try to make it fast, at least like on a naive approach. It's not measured yet, it's not like battle proven, but it's like a draft that was implemented in mind with, hey, let's write what I want to write, but try to be as memory concerning as possible. At some points I did not, but it's still fast enough currently. And yeah, that's kind of like the way where I want to have it fast. I want to have it reliable. So I don't. Reliable is a word that's maybe it was not wise to use it, because we can't really rely on anything, because at the end it's gonna be a malloc. No matter how fancy you are, at the end the weak point is, or the not weak point, because it's battle proven and always in there. Every operating system can do it, but at the end it's gonna be a malloc. It's the OS that's involved. It's everything. So I don't want to say too much reliable, but I do kind of like wanted to implement a system that kind of like withstands all like load cases. No matter how many allocations you want to do, it shall always in the end hold up. Let's say it like that. I don't want to go too much into the details. It might be unwise that I told that word, but yeah. Next thing, secure. Why do I want to have a secure memory management? Well, I want to have it being secure for handling faults. Now, in general, what can happen is, especially if you're writing a web application, there could be at some point a problem. Let's just don't even put the problem in the framework. Let's imagine the framework allows you to handle strings. It's a very simple thing, but handle a string, a combination of characters. Now, what could happen is that a API builds on top of that, on a framework. It gets the data from the API endpoint. The API endpoint tells the API, hey, I want to now transmit a large string to you, and the string should be 1 million gigabyte big. Now you already see the thing, right? If you're writing a naive framework, the API would see that limit, would maybe not care at all, would just, because nobody has implemented that, and actually in my framework nobody should need to implement that, because it shall be simple. You should not kind of like boilerplate your code up to that. It should be other mechanisms that catch that, like validations, form validations, and even validations for API endpoints and for JSON data. But let's say something has gone through these mechanisms and it's not checked in the code, right? The code framework forwards to the framework, hey, allocate me a string of that size in a kind of like context, in the context that's shared between certain requests, that's shared in a session. That's something that I want to have. I want to have session stores. And I want to say, all right, I want to now put this 1 million gigabytes big string on that session store, which would then mean on a naive framework that somebody would try to construct the STD string and reserve that size, which at the end would mean that it goes to system malloc and allocates this memory, which would fail for such a high number. But let's maybe be a bit more substantial. Let's say somebody requests a gigabyte big string. And if you're trying to bring down a web app and you find out you can actually ask the string in the ever size you want, you're always going to get a, okay, you can do it. Well, I'm just going to start I don't even think that you need to do a DDoS. You can just start a denial of service attack. Oh, no, man, I know I'm on. I'm not going to tell you how it works, but in general, it could happen that more memory is requested than that can kind of like be served, and you're calling malloc with every time a gigabyte, which malloc will not complain about, because like it's in the valid range that the system has, but at some point it's gonna swap. The server's gonna get slow, and at some point other allocations will fail and the server will crash. Boom. You have a normal connection, nothing has went wrong in the framework, but like just because the API was written badly, it can now be abused and the server cannot recover from that. That's not something that should happen. So this is why I want to have a secure way. I want to implement, or I have implemented, a so-called monitored allocator where you can tell the maximum number of bytes that are allowed to allocate. So if you have like a session store, you tell, all right, you have a configuration file that says, all right, the session store can be at maximum 32 megabytes. The single session that's connected to the server, a single HTTP transaction, can have a maximum number of, let's say, like 125 megabytes. Then you basically tell these allocators that this is the limit, the total limit that they are allowed to allocate. These are sub-allocators of like the big one global allocator. And then they basically will throw as soon as you're trying to exceed it, which will terminate the session, which will give at the end like a bad request error on HTTP, probably bad request, internal server error, depending on what's going to be configured and how I'm going to implement that. But it's not going to take down the server. Like there's gonna be a HTTP request that's parsed, then it's handled to the user code. The user code gives me the response, it's sent. If in the user code, or while the user code is executing, something went wrong, like this allocation issue, well, it's gonna be logged. We're gonna construct a replacement response and send the replacement response to the client and say, hey, there was an issue. This is not how you're allowed to use me. Everything is good. No errors, no bad patterns that try to access the server. Nothing in the end will happen. The server will still withstand these requests and everything is good. Now, fault recoverable. Well, what's the problem? Even if I have an allowance of 125 megabytes per session. Well, what could happen is that there's a memory leak somewhere. In theory, this should not happen. But let's just imagine somebody uses the API of the server in a wrong way, or maybe there's a bug in the server that's been trying to be exploited. Oh, bad words that YouTube doesn't like. But there's kind of like an exploit in the server, and you're kind of like trying to leak memory. This is something that should be recoverable. How can we make a recoverable, how can we track, or how can we make memory leaks recoverable? Well, there it comes, the monitored allocator with a memory tracker. The memory tracker will track every single allocation, which of course is slow. It will track every single allocation, when it was allocated, how many bytes, for which purpose. It will track them, and it will also track if they have been freed. And only if all of them have been freed, the whole transaction was successfully. So what you can do is you can have a memory tracker and a monitored allocator, and as soon as kind of like a session has finished doing the HTTP transaction, you are doing a cleanup, and you basically tell the memory tracker that it shall check for leaks and fix them. And then the memory tracker will iterate through every allocation that has been made. It will check, has this been cleared? Has this been cleared? Has it been cleared? Oh, it has not been. Okay, so now release the memory. That's the whole idea. We want to have it all deterministic and safe and fault recoverable. If there's a fault, we don't want to have the whole server go down. We want to log something and say something went wrong. But I want to be able to see that that there has been something that went wrong, and kind of like give the response back that there has been something wrong and fix it. So that the problem is, right, if you have a memory leak, we have no longer the acceptance. If I have a monitored allocator, which is what I've implemented, you can actually see at the end that if it monitors that there's still more than 0 bytes allocated, well, nice, we have a memory leak, but it has not been fixed. So I want to be able to fix memory leaks when it is required, which is going to be at session stores, which is going to be at actually HTTP sessions. In general, HTTP sessions is also like a bad thing. Sessions I kind of like use differently, but like TCP TLS sessions, they will in the future be able to kind of like find and fix their memory leaks, and yeah, there are kind of like some implementations that are going to be planned there that do it, and the actual infrastructure is already there. Now, let's get now actually started taking a look at the code. The first thing, the most basic thing, is the memory allocator. Memory allocator is basically just defining how mallocs and frees work. Now you can actually see that we are overdoing it here. We have a size of the block that we want to have, and we have the type for which this block is allocated. So you always need a type, even through if you're just supplying like void pointer or anything like that, that doesn't indicate anything. But you always need a type. Then we have a deallocate that's also requiring the block, the size, and the type. So if you're deallocating it, we actually need the size of the allocation. Is this an issue? No, because the standard library brings us that out of the box. And if we are taking, or if we are making sure that we are always using the standard library, like the standard new, allocator traits, make shared, make unique, if we are only using these, it's not an issue at all. If we're using bare minimum, allocate and deallocate, we just need to come up with our own types that fit. That's the whole point. Now, on top of this memory allocator, there's a C allocator. That's a plain old allocator. Basically, what this does, it just redirects to malloc and free. There is a, it's actually a singleton, and it has an instance that can be retrieved, but this should not be used. And I do want to put in these. In general, this is basically just a wrapper around malloc and free using the memory allocator interface, which is required because we are later on, of course, want to chain allocators together, and we need to have a point we can start our chain, which will be our C allocator, malloc and free. On top of that C allocator, there will be the basic allocator. The basic allocator is an allocator that actually not implements memory allocation at all. It just implements basic functionality around an allocator. Basically, it handles the parent management, right? It requires a parent allocator, which is by default the C allocator. It's stored in here somewhere down here is the parent allocator. It allows access to the parent allocator, and what it does, it kind of like allows access to make shared, make unique, creating new objects and deleting objects, which are in general all working the same, using the allocator traits from the standard library and a custom implemented allocator that will be constructed on the base of the memory allocator of the interface and then be used with the allocator traits. I'm going to go to these later on, or let's actually go into them now. Now, CPP SCD is just wrapping around the standard library. Now, the first thing is the allocator. This is a custom allocator for the standard library. This requires the value type and size type. They are actually templatable, or need to be templates, and actually the template is the kind of object that it is allocating. So this is why I also have the type information available. Now, you can see that the allocator requires a copy constructor from a different type, which basically will pass on the allocator from the first one to the second one. In general, the allocator pointer is stored as a pointer, and you can have a default constructor that's also important, and you need to be able to assign them around to convert them to kind of like different allocator types. Now, maybe there in the future is going to be some implementation that's making things even more like the problem that could arise with them if you're now using an allocator that's kind of like having a fixed allocation size and you're trying to allocate something larger, it will give us an exception. So then we might implement something that kind of like allows an allocator to downgrade itself to the parent if it cannot fulfill the allocation request. That's the whole idea that's going to happen in the end. A downgrade function that basically downgrades the allocator until it can fulfill the request. That's something that might be implemented in the future as well. Now, the actual meat is the allocate function. Well, if there's no allocation, we have a bad allocation. If we have an allocator, we are creating, or we're actually calling the alloc function on it with the actual size and the type that we are trying to request. If this fails, we throw again. Deallocate simple. We also have the number of objects that we want to deallocate. The standard library works like that. Don't ask me why, really. Probably because they want to allow you to track memory usages. So basically just calling around. Now, we do not need to check these again because deallocate, by the means of how the standard library is built, will only be called if there was a successful allocate. So yeah, that's why it is like that. Max size is the maximum size that it can allocate. You can basically just see, or the maximum count that it can allocate is just it's some boilerplate code. In general, this should be implemented in a proper way. This now allows like skyrocketing allocations. But in general, we have monitored and checked allocators that can later on restrict. Now we have access by the get memory allocator interface. Now, allocator comparison should also be implemented. This is done down here. So this is where this happens. Now, on top of this allocator, we are building CPP SCD memory. So we are now using this allocator to implement a make shared. and the make unique function, and we are also building aliases for the shared pointer and the unique pointer. The shared pointer, yeah, it's simple. Just use it again. The unique pointer actually requires a custom deleter that I am defining like this. Now make shared is actually quite simple. I don't know. This is actually, it's quite simple. Yeah, it is quite simple, but I didn't know how to do it. Oof. This is why I've asked ChatGPT. I am not sure. I don't think that we need this rebind allocator. Not sure why ChatGPT uses that. And I wanted to actually put a bit of more research, but I don't have time. I need to get the videos ready. I don't think that we need these, and I don't think that we need to have like doubled instances of the allocator to rebind them to a different type. I don't think so, because my allocator is created here with the certain type. So I think this line could be deleted and this line could be deleted, but I was not bothered to check previously. And then use the base allocator instead of the rebound allocator everywhere. In general, how this works is that we are first using the allocator traits, which is basically a uniform way to use SCD allocators. We are using this to access the rebound allocator and allocate one object. Well, how do we, what kind of object do we allocate that when this has been supplied to the allocator and thus to the allocator traits? So this is basically now calling malloc, or the allocate function from the interface. At the end, it's going to call malloc, and then we're going to try to construct the object. If that fails, it's a bad allocation and we deallocate. If this succeeds, we are constructing a new shared pointer with the new pointer with a custom deleter. In this case, I don't know why this is mutable. It's also something that I tried to find out. We are passing on the allocator that's required for destroying it. Maybe this is why we need rebinding, but I don't really think so. Which is basically destroying the object, calling the destructor, and deallocating the object. This is basically what happens when destroying the object. This is the pointer, and what we also need is the allocator in here, because I think we need a control block for the shared pointer. Not sure of that though. That basically handles all the reference counting. Yeah, we need it, but it could be also that I don't know. We will probably need it. The shared pointer needs a control block, so this is why we have it in here. Right. Okay, so unique pointer works actually quite similar, only that the function is different. Everything works the same. Allocation, it's like shared and unique is the same. The only difference is the constructor, that this one does not require the allocator once more, because it's not having like a control block. It's just gonna pass around the deleter function that has been implied here. So if it is distracted, it calls that. If it is kind of like moved, it moves it from one place to the other. That's kind of like the main story behind these, but they are quite similar. The next thing that's interesting is the CVV containers. It's basically just a remapping of all containers that we need. We have a string container, so we are remapping the basic strings to, well, the same like the standard library does it, but using the custom allocator. I have a basic string init that allows us to initialize basic strings and also pass on the arguments to the constructor, because, well, first we have the arguments, then we have the allocator, but I need to construct the allocator based out of my allocator interface, so that's why I've made a function that makes this a bit more handier. I've remapped like all the types of strings that we have. Same goes for vector, unordered map, list, and queue. These are the types that I'm currently using. If I use something new from the standard library, I'm just going to add it in here. It does require a bit of work, but in general, it's not really some magic that's going on here, just a bit of helper code and some remapping to tell the standard library that we are using custom allocators. Now, this is how I basically force the standard library to follow my way of allocating. And yeah, that's it. Now, on top of this basic allocator, I have built the monitored allocator. This is now the actual first allocator that does some work. Now, this one is actually quite complicated because a monitored allocation can internally have multiple results. Now, first is the result pass, which means that the monitored allocator can use its parent allocator to allocate, but it can also have different results that basically tell us that something has happened. First of all, there's the allocation limit, which means that the maximum number of allocations, not bytes, the total number of allocations has been exceeded on this allocator, and thus the allocator can no longer allocate memory. Then we have the memory limit. If we have reached the maximum number of bytes that we are allowed to allocate, and the next allocation would no longer fit. This is also some outcome that can happen. Then there is something called the block limit. So we can limit one block of allocation. For example, if we are going to a pool allocator, we can use a monitored allocator to limit to the size of the elements of the pool to make sure that no memory allocation larger than one element size is passed to the pool, or it is passed, but it's going to fail then. I've also implemented very quickly a type limit, but that's not really something that should be too much of a concerning right now. This could be if we have like a customized pool allocator that's kind of like fixed to a certain type, so we can kind of like limit it to only allocate objects of that certain type, which in the future might prove useful actually. So we can just basically tell the allocator that it's not allowed to kind of like allocate anymore. Now, what we also have is a parent allocator failure. If the parent allocator cannot allocate, we have that. I'm not sure if this is even required, and we can remove that because I went exception based and stuff. All right, so what I also have is I have a function that can convert, these error codes into explaining strings. This is used for the monitored allocator exception. So if something goes wrong in the monitored allocator, we have a reason, a size, and the type that we are trying to construct, which will basically in the constructor using this function that generates the text for the codes, just use like FMT to kind of like get a message why it failed. Now the monitored allocator has a few quirks that you need to be aware of if you use them, or I need to be aware because it's not available yet, the code. But in general, it supports allocating and deallocating, and what it also supports is setting limits. It sets the allocation limits, it sets the memory limit, the block limit, the type limit, and as soon as a limit is set, it basically tells itself that it has at least one limit, so limit check shall be enabled. This is a monitored allocator, which shall be also be usable for just memory monitoring, so I don't want to kind of like put too much load to doing like many ifs, so I have a bypass over all the checks. The next thing that you can do is you can set a tracker. The tracker will get or will keep track of all memory allocations and allows for leak tracking and fixing. Then we have a way to get the usage of the allocator, so the actual memory usage and the allocations count. This is stored in an atomic, so this is thread safe, this allocator, at least for like allocating and freeing. In the most cases, the memory checks are not thread safe currently, which they might be in the future due to security reasons. But currently they are not thread safe. Do they need to be thread safe? Depends on. If we have one monitored allocator per connection, we are safe because there's only going to be one thread per connection. Also, just one thread per like session. Now that might be true actually, because they can have like multiple connections that are accessing a section a session in one time, or a session store at one time, but like at least the sessions, it's not an issue. Now internally, it provides a few functions. It provides a function called check allocation that's overridable by the user, so that you can actually, if you're building a custom monitored allocator, you can provide more checks that can have results. We also have the monitor allocate and the monitor deallocate function that is going to basically monitor if an allocation has taken place and monitor if a deallocation has been taken place. We have a storage for the limits, we have a storage of the usages, we have the tracker, and if the limits are active. Now, how does all of that come together? First of all, the allocation function. Now, first of all, we are evaluating the allocation. Can we do it? If we can, if we pass, we allocate with the parent allocator. We monitor that we have allocated and we return the pointer. If we did not pass, we can throw the exception. Deallocate is more simpler. We are monitoring that we are deallocating, and then we are getting the parent allocator and we can deallocate on the parent one. Now, how does check allocation work? Currently, it just checks if there are checks. If there are no checks, we are returning pass, or if all checks pass, we of course also return pass. Now, internally here, it's actually quite simple. If the size of the allocation is bigger than the block limit, we return that we have a block limit reached. If the allocations count, so how many allocations we currently have, plus 1 exceeds the limit, we return that we have an issue here. Now you can actually see if we have two concurrent threads that are kind of like currently in the checking process, while this one has not been changed, it could be that multiple pass with multiple threads. So actually we would need to be away from atomics and completely back to log-based allocation on an allocator, which I might do in the future. But currently this works for me, and if I need the allocator to be completely 100% thread safe, I'm going to go back to log-based. Now, down here we have the memory usage. That's working the same. We are adding the size and we're checking if it's bigger than the memory limit. The type limit's also simple. If the type limit is preset and they don't match, well, throw the type or return the type limit result. Now, monitoring the allocation is also simple. First of all, we do fetch and add. So we are basically adding 1 to the allocations and the size to the memory that we are using. Same actually goes for monitoring the deallocation, just that we didn't use subtracting. So we are adding 1, subtracting 1, adding size, subtracting size, so that we always have the correct size and usages on record in the atomics. Now down here, in both of these, we are also considering a so-called tracker. If we have a tracker, we are tracking the allocation with the block that we are allocating, the size and the type. And if we are deallocating, we basically tell that we deallocated the block. Now, what the hell does the memory tracker do? The memory tracker tracks memory usages. So there's a memory track. This is the fundamental type that it's managing. It has a block. So which block is being tracked? The size of the block that's being tracked, the type that's associated with the block, a boolean that indicates if the block is still allocated, and we have 2 system clock time points that indicate when it was allocated and when it was deallocated, because I want to also keep track of memory usages. How long was the memory alive? If I have a memory leak, when was it allocated, and things like that. The memory tracker itself is simple. It tracks allocation and deallocations. It has the count, report, and fix leaks, as well as the clear tracks function and a set logger function. This is a bit of an exotic function. You can actually set a logger, and depending on if you have a logger set, it will trace. If no logger is set, it will not trace. However, if no logger is set, it will use for critical errors the default logger, and if it's set, it will also use the set logger for critical logs, which is a bit of a madness that's going on in that function. But yeah, in general, like track allocation, track deallocation, then there's a count, report, and fix leaks, which also requires the allocator to fix on, and we have clear tracks, which basically clears all memory tracks. Don't know, I think this one is not clearing because it will just fix. So yeah, how does that happen? Track allocation. First of all, we have a bypass that happens if actually this non-fixable memory leak. Basically, as soon as we are as soon as we go into fixing the leaks, we are no longer thread safe, which means that we are bypassing the trackings, which means that we have an unfixable leak, which we could use critical in here, right? Because this is something that should not happen from the usage pattern. The tracker shall be created, the allocator shall be created, then some code shall be called that uses the allocator, and as soon as the code returns that uses the allocator, it shall check and track the leaks. So yeah, this piece of code is shall never be reached at all. Now, a memory track is quite simple. We just supply all the data, and if we have a logger, we trace, and then we can just go into the critical section and put it back on the tracks. This is actually a list. Then we go to the track deallocations. If we are bypassing, this is actually expected that this is logged. This is expected since the tracker is cleaning up leaked memory. So every memory that's leaked and deallocated will of course still call the tracking function. But since we are currently on fixing them, we do not actually use it and go into the critical section. Directly returning, and we are keeping track of it. Now, down here's the critical section. Now this is actually the bottleneck of the tracker, because every free operation, every deallocation needs to find its corresponding allocation. However, we are using a list because we require the order, and we cannot use an unordered map. And I also didn't want to do the madness with having 2 containers, one for access and one for ordering. It doesn't make sense. I was going now for a list. Now the list is actually traversed from the reverse. It's reverse transferred, so from the back to the front, because it's very likely that a deallocation will happen in the reverse order. And also, if you have allocate, deallocate, allocate, deallocate with a pool allocator, you might get the same memory address multiple times. So you always need to find the last allocation that fits the deallocation. then it's safe against allocating or having multiple allocations that return the same memory address. So in general, we just reverse traverse it. If we are finding the block, we are saying it's no longer allocated, and we are setting the deallocating time, and we are doing tracing, and we are returning. If the block is not in here, we actually warn, which should be an error. The memory block was deallocated but not found in memory tracker associated with the current monitor allocator. This is bad if this happens, so yeah. But I don't know what I'm gonna more into the details on what's going on here. Or at least in the error message, you know what's going on. Now the next function is the count, report, and fix leak functions. This is now trying to find, it's tracking down memory blocks that have not been deallocated yet, and it's gonna deallocate them. This is why it requires a memory allocator, because it actually doesn't know. This class doesn't know about the allocator. The monitored allocator gets the tracker, but as soon as the tracker shall clean up, it requires the allocator on where to free the memory. Now, how does that work? Well, first of all, it does a bit of logging, then it enables bypassing, then it goes into a for loop through all tracks and disables bypassing, because this is not actually the work where it might be deallocating. Now, first of all, it checks if it is allocated. If it's still allocated, it will be deallocated on the allocator by using the stored block size, and the block type. So we know all the data. We know how the deallocation call would have looked like if it was valid, no matter where it was coming from. If it was coming from some user function, some shared pointer. I mean, this could kill a shared pointer. So the shared pointer would throw an exception, but yeah, I hope this will not happen. It could happen though, but maybe it did not. I don't know. But still, this is kind of like fixing memory leaks, but it's... You shouldn't use a shared pointer with a tracker attached to it, because the shared pointer cleans up itself and there's stuff gonna happen that makes it sure. Like, this allocator is only safe for stuff that's then inaccessible. It warned on the critical logger that it detected and fixed the memory leak. This is only a warn. It's gonna give you some details, like the type, the size, the block, and the allocation time when it was created. Then it will say that it has been allocated to false, and then the deallocation time is also tracked, and we are incrementing the leak count. In the end, if we have the leak count, we are warning that we have memory leaks and the number of memory leaks. And if it's not the case and we have a logger, we just trace that we found no leak. Clear tracks, simple. Don't need to go into which details. This is how the logger works. The logger is assigned. If the logger is existent, we are using it for the critical. If it's not existent, we are using the default logger. So very, very simple code around that. Now, the monitored allocator is also used as the default allocator. It's used as the default allocator type, which is currently the monitored allocator. And then there's a function that basically has a static instance of the of one monitored allocator as the default allocator, which, since we don't provide anything as a destructor, uses the C allocator as its parent. Quite simple. Now, on top of the monitored allocator, we have a pool allocator built. I don't want to go too much into the detail. Basically, this allocator allows you to always allocate memories of the blocks of the same size or smaller than the specified size, which is done by using the block limit of the memory allocator. The implementation is actually quite simple. You can see just 130 lines of a custom allocator that is way faster than the standard library. This kind of allocator is going to be used for like the buffers for the I/O operations. Like, there's going to be a maximum size of the HTTP headers, and there's going to be a pool allocator that's just responsible for allocating HTTP headers. We might also have an allocator that's also sending and receiving data. For these, maybe only sending. Receiving is a different story, because the payload can be different, especially if you're receiving files, but still there might be a maximum size associated with that. So we're going to have a pool of the maximum size there as well. Maybe we have one pool for the headers and the data, but this depends on how I'm going to implement that. Or we have multiple pools. It's not an issue to have multiple pools. These pools grow automatically. They're using the parent allocator to allocate themselves. This is more or less C code what I have implemented. implemented here. This is not object oriented at all. These are just structs that are abused. This makes this fast. And I don't know how safe it is. There's still some checks that might be implied, and I need to revisit that. It's not used at all currently, so not a big deal. All right, so quite some stuff. This is how it gets together. This is the default allocator that's used. We can actually quickly create a memory tracker so that we can actually show you how this all works. So let's use the tracker, the memory tracker here. And let's quickly put a memory tracker on the allocator. Memory tracker. Now the tracker requires an allocator itself. I do not want to use the default one, or do I? No, because we do. Can we use the default allocator for the tracker as well? I don't think that's a good idea, actually. Nah, it's not a good idea. This tracker shall use... Now, in general, the default allocator will never be tracked. It's just something that I'm now going to do for you. The default allocator is meant to be the lowest level and lowest checked level of the API. This is not going to be a tracked allocator. But let's get an instance of the C allocator and use it here. And then let's use the alias for the default allocator and set a tracker on it and provide this tracker. Now we have a tracker in place, and if I run the code now, you can actually see every allocation that's currently done by the library. Let's see. Oh, I have not done this actually. Quite interesting of what allocation schemes we're gonna get. It's gonna compile a bit. What the hell? Why are you not working? Huh? ASIO basic socket acceptor. It's the IO context, right? That's failing me now. Like, this is ASIO. This is templates. This is ASIO. I don't know what happens because I do have dealt a lot with this template shit in the past. This is in server. TCP endpoint.ctp. This is the one that fits. ASIO IO context. Now the TCP acceptor, let's see. Basic socket acceptor TCP. So how does your constructor work? Execution context. Protocol, oh damn. I think that's it. That's the one we are talking about. It does require const references, which don't see a problem then with the code. Is it really that one? Like TCP... No, TCP session. No, it's not compiling TCP session. I'm talking bullshit. TCP endpoint.cpp is compiled. X memory. Const. Damn, do we have the issue here? Huh. Yeah, of course we have the issue here. Because that's the one that's actually now passing this on to the class that we are implementing, which goes to that make unique, which goes to that one. Yeah, was right. What are... Do I need to just be explicit because I'm dereferencing a pointer? ASIO IO context. No. Do I don't know. I don't think that I need a reference wrapper here. Or do it needs to be const? Is there a const reference wrapper? There shouldn't be. Const. No. Why is that not working? I mean, I need to fix that. But I don't want to bother you now with that. And this is now completely... I mean, this one worked, right? So if this one worked, why shouldn't it work for me? Yeah, I'm just going to use that one. Needs to be 100% cautious. I know what I'm doing. So, yeah. This is how we start. We're starting with no memory allocations at all. And then as soon as I run a request, you can see a bit of logs. But I don't see memory allocations. Why do I not see memory allocations? I should see some. That's odd. Because there's no logger set on the tracker. I told you that I need to set a logger on the tracker. Tracker, set logger, SPD log, not get, but SPD log default logger. That's how it needs to be done, so that I also get my memory traces. All right, there you can see. Now we have an allocation here. Recording memory allocation for the container proxy, and this is the container proxy for the queue. And then when I start, you can see that we are getting a hell of a lot more log messages. You can see that actually every connection is getting allocations and deallocations. Let's start with the first one. Now, first of all, you can see that we are now recording memory allocation of 824 bytes for type class TLS session. So there was a session created. Then we had a handshake. Then we had another allocation of TLS session. That's interesting. Why do we have another one? Probably because we are putting it in the list. Huh. I don't know. We have another one. I don't know why this one is in here. We would need to hunt this now down. What is happening here? But I suspect that it's fine. This is all during the memory allocation of the session. The session is created, handshake. Then we have the next session. That's, I think, that one. Memory allocation, and then we have a session. We have two sessions at the same time. This is why this happens. So we have this one. Session is created. This is the memory for that session. Then we have the TLS handshake. Let's ignore that one. This is the first successful for the S05. Then you can see that we are getting an allocation of the queuable session pointer, whatever. This is basically what's been put in the queue. Because queuable session, that's how the queue manages, is a list. And then you can see that we have another allocation, but this is probably for the 06. TLS and shake 05. 06 is successfully here. Okay, all right, this is allocation, and then we have deallocation, right? Because we are processing one RZO event, which basically means that we have allocated the session, put it on the queue. Now we are closing the session, so the session gets destroyed. Then the next IO operation comes. The handshake was successfully, and the session is directly closed and deallocated. Yeah, it was not put on there, but you can see there's like memory lifetime and stuff. In general, later on to stabilize a bit, this makes it a bit more easier to analyze. We have first the memory allocation of the session, then we get the feedback the session has been created. We are starting the handshake was successfully, and then we are closing the session, so we are deallocating the session. You can see that it's no longer going on the queue, or it seems it's no longer going on the queue because the queue is actually reusing its memory that has been allocated here. Like this allocation and this allocation is what's been reused. And now we are here. And what we can do quickly to also show you how this works. This is now going to spam our console, but what we can do is we can add a quick info logging about the memory usage. Memory usage is going to be that one, and this is going to be the allocations. So the number of allocations in here, and then I can just take my allocator, because it's a monitored allocator, can get the usage, and then we can get the allocations count of the allocator, and then we have a bit of an information on what the memory usage is every time we are kind of like running our stuff. So you can see after we have started up, the memory usage is 60 bytes, which is the number of allocations as 1, which is the container proxy. Now, if we are making our request, I'm not quite interested why, because we are run once, right? That's nice. You can see every time we are getting a log now is when RZO has kind of like run once. You can see that after the first session is created, so we have 2 allocations, then it runs, then there's another allocation going on here for the next connection, which you can now see that we have 3 allocations with these numbers of byte. Then there's the first handshake that was successfully, which means that we are allocating stuff, and we're also deallocating with something because the session has been directly closed. You can like see that we have now 4 allocations because we have 2 allocations with like 3. 2 times allocate, 1 times deallocate makes 4 in total. 920, it's a bit less. And then you can see at some point this is also going to stabilize again, where we have like the memory usage of 3 allocations. Then while we are kind of like processing the request, so while the session is living, we have 4 allocations, and then after the session is destroyed, we are back to 3 allocations, which you can see that it's kind of like making sense. You can actually see that the actual handshake does take a few RZO runs, because actually, I don't know how many, I'm not out of my mind how many steps are involved in a TLS handshake, but basically it's a bit of a back and forth between the server and the client, and this is probably 1 by 1 and queued on the RZO queue. So that's basically, it's probably waiting for a hello from the client. Maybe, no, it's the first the server hello. There might be first the server hello, then there's a client hello, then the server is kind of like transferring the information. I don't know. Don't let me guess. I'm just going to tell you wrong stuff. Don't let me guess. That's not a good idea. Right, you can kind of like see what happens, and if maybe I can load the server quite some more times. Can I bring more load on the server so that we have more allocations now, because our server is already too deterministic, because we are only processing once. 1 at a try, only 1 allocation at a try. We're only processing 1 RZO request at a time, which, as you can see, makes our server way. Look how predictable this is. This is what I'm talking about being predictable. Of course, if you have multiple threads, it's getting way harder to predict, but like this one, how like one session works is like 100% deterministic and predictable. If you know all the odds, then you can spam your console with stuff. Yeah, that's it. So this is what I've implemented. A lot of memory tracking. I hope you did enjoy it. Was again a bit of a longer video, but now at least I have like 2 videos that I can upload while I'm away, and you should have a bit of a value and a bit of an insights on how this works. So yeah, quite some stuff done. Thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. Bye.